Tonight's lesson is going to be focusing on the mechanical energy module. We're going to be talking about the law of conservation of energy and then also power. A conservation force results in all the work done being stored as a form of mechanical energy. It can be converted from one form of mechanical energy to another. Non-conservative systems is when energy is lost. An example would be a heat loss from friction. Mechanical energy is lost in the system. It doesn't get destroyed. It is just converted into another form of energy. Remember that the law of conservation of energy states that energy cannot be created nor destroyed. So if we look over here in our diagram, you can see that energy can be transformed from chemical to motion. So this is the sugar in the food converting into that motional energy of pedaling the bike. We also have radiant energy, which is solar energy, converting into chemical energy. This would be a process of photosynthesis. If you've taken biology, you should know that. Another example of chemical motion would be chemical motion of the fossil fuels, and gasoline will fuel empower the car to go. And then also we can convert electrical energy into thermal energy, which would be heat energy. So these are just some examples of demonstrating the law of conservation of energy, of how energy can be transformed from one form to another. If there is no friction present, so on a frictionless slope, energy is converted from the potential at the top of the slope to kinetic at the bottom of the slope. No energy is lost as heat because there's no friction. So remember that in this kind of system, you're going to have a total energy equal to each other because none of it's lost as heat. So the potential energy will always equal the kinetic energy. If friction is present, there's going to be a negative work being done. So at the bottom of the incline, it would have less kinetic energy without friction. And the reason why is because some energy is being lost as heat. That's why there's going to be less kinetic energy at the bottom if no friction is present. Mechanical energy is independent of the pathway. This also known as something called a state function. So this value has nothing to do with how the box got to its state. If it doesn't matter how the box got there, then that means it can be considered mechanical energy. There are some exceptions of the law of conservation of energy, and there are three: nuclear fission, nuclear fusion, and radioactive decay. This is when energy is converted into matter or matter into energy. So this is either when atoms are being split or atoms are being forced together with a chemical bond or radioactive decay. So energy is being lost in the system because matter is being created or destroyed. I shouldn't say destroyed, broken apart. All right, now we're going to be jumping into the practice problems. So the first thing that we need to do is be familiar with our formulas. And let's analyze this example together. So we have a 5 kilogram ball. A 5 kilogram ball on top of the ramp that is 10 meters above the ground and has initial velocity of 7.50 meters per second. The question is asking for the total mechanical energy at the top of the ramp. So a total mechanical energy would follow this formula, which is energy equals the potential energy plus the kinetic energy. We also know that a formula for potential energy is mass times gravity times the vertical displacement, and that's what Y stands for. And then we have the kinetic energy, which is 1/2 mass times the velocity squared. So we plug in these two components into the total formula for energy. This is a new formula that we can use. Then we plug in what we know. So the mass is 5.0 times gravity, 9.8, which is a constant, times the vertical displacement of the ramp, which is 10. And then we're going to add that by 1/2 times the mass again, times the velocity squared. Follow the order of operations, plug that into our calculator, and we should get 631 joules for the total mechanical energy of the system. Same scenario, but now it's asking what the total mechanical energy at point 5.0 meters above the ground. So we're starting at 10 meters, but it's asking for 5. Obviously, I'm guessing here. But remember that since this is a frictionless surface, the mechanical energy, or the total mechanical energy on the system, since that's going to be lost from in the form of heat as friction, should equal what we just calculated. So it's going to be 631 joules. Don't let that type of problem trick you. The next part of this problem is asking what is the velocity of the ball when it is 5 meters above the ground. So again, we have that 5 meters. We're going to use the same formula that we did in that first problem. We now know the total energy, 631. Plug in what we know, 9.8. Now we're at 5. Remember, that's going to be the vertical displacement plus 1/2 mass, which is 5, times velocity squared. So now we don't know this velocity. We simplify both sides, and remember to do the inverse of a square. We're going to take the square root of both sides. So we take the square root of 154. We should get approximately 12.4 meters per second for the velocity of the ball at the height of 5 meters above the ground on the ramp. At the bottom, it runs into a spring and comes to a stop. What is the total mechanical energy at the bottom of the ramp? Remember, it's going to be the same because nothing was lost as a friction. So when the ball rolls down, it's going to be the same total energy. So again, 631 joules. Again, don't let that type of question trick you on the quiz or the test. All right, another part of the problem is if the spring constant is 500, how much is it compressed? So again, we have to think about what we know about the spring constant formula. We're going to plug in that the energy is 1/2 K times X, which is the compression. So we plug in what we know, 631 joules times 1/2 500, which is the spring constant, times the vertical, or the distance, I guess. I was trying to say horizontal distance, but the distance of the spring compressed. We plug in what we know, and remember again, the inverse to the square, we take the square root of 2.524, and we should get 1.59 meters. All right, now we're going to move into the topic of power.